Hello, my name is Carlos Hinojosa and I will present our work on learning privacy-preserving optics for human pose estimation. We have cameras everywhere and this overwhelming amount of visual data has boosted vision research in the last 2 decades. However, the widespread use of the camera has led to increasing concern in computer vision community about users' privacy and security. In this work, we focus on the camera hardware to tackle this problem. Traditional cameras capture visual details that could lead to privacy issues. In this work, we learn to design the camera lens to hide the details of the scene. The distortion we learn protects privacy and allows us to extract features from the acquired image that enable human pose estimation. Let's consider this traditional human pose estimation pipeline with a camera that acquires high-resolution non-private images and a set of convolutional layers that extract features and estimate the human pose. Some prior works on privacy-preserving vision propose to use low-resolution images to hide the identity of a person. However, with such an approach, the acquired images lose a lot of information which make the human pose estimation not accurate. Other works have used the focusing lens to blur the images and protects the user privacy. However, this approach is susceptible to reverse engineering attacks, as we will see later in this presentation. Another approach to privacy-preserving vision is to use depth cameras to only obtain the depth information of the scene. However, the imaging sensor of the depth cameras can be saturated by sunlight when used outdoors. In general, these approaches use a fixed optical system to distort images. Specifically, the camera is designed first without considering the final vision task. The key idea of this work is to jointly design the camera lens and optimize a human pose estimation network to protect privacy along the computer vision pipeline. Let us now look at our method in detail to understand how we achieve privacy-preserving human pose estimation. In general, the imaging process can be formulated as a convolution between the scene and the point spread function of the camera followed by reconstruction. The PSF describes the response of the camera to a point source of light and determines the image quality. If the lens has defects or optical aberration, the quality decreases since the aberration causes light to spread out instead of focusing to form a sharp image. When training a human pose estimation network, each part of this pipeline is defined separately. First, optical engineers optimize the optics or image acquisition system to minimize the lens aberration. Then, once we get a high-resolution camera, we acquire multiple images to train our human pose estimation network. Recent work in computational photography has introduced the joint design of optics and algorithms to boost the performance of the final task while keeping the high quality reconstruction. In general, such work focuses on removing the aberration from the lens to obtain high-quality images. In this work, we rely on the converse approach. We want to maximize the aberration in the lens to obtain a highly degraded image and provide privacy protection while obtaining a good human pose estimation performance. Our optimization process has two parts: an optical encoder, which provides hardware-level privacy protection by degrading the image quality, and a CNN decoder that learns features from the highly degraded image to perform human pose estimation. Let's first zoom into the optical encoder. Our optical system consists of a camera with a thin convex lens and a refractive optical element add-on. Our optimization searches for the parameters that define the surface of the refractive optical element. Then, the PSF will also change depending on the surface of the refractive optical element. Let's analyze how this surface profile is defined. We parameterize the surface profile with Cernic polynomials. Each polynomial describes a wave from aberration. Then, we define the surface profile with this equation where Cj are the Cernic basis and alpha j are the Cernic coefficient we want to learn. Therefore, different from common deep optics approaches, our end-to-end training finds a set of coefficient alpha that provides the maximum visual distortion of the scene but allows to extract relevant features to perform human pose estimation. Now, let's zoom into our decoder. To perform the human pose estimation, we adopt the OpenPose network. This network is composed of a backbone and a set of convolutional layers that detect key points and their relationship. In this work, we don't train the OpenPose network from scratch. Instead, we use the pertaining model and fine-tune some layers. Also, we split the output feature into the body and face related parts and only use the body features in our optimization. Our optimization problem combines two goals: to visually distort the image and to perform the human pose estimation. The result of the training process is twofold: the camera lens parameter alpha, which determines the aberration added to the lens, and the parameters of the pose estimation network. Here you can visualize the optimization process where face recognition and image quality decrease while our network still estimates human pose. We train our proposed end-to-end approach on the COCO dataset. To evaluate human pose estimation, we use the object key point similarity metric. We report the standard average precision and recall scores. We use an implementation of the ArcFace network to perform face recognition and measure privacy. We train the ArcFace model on Microsoft Celebrity dataset and measure face recognition performance in terms of the area under curve of the receiver operating characteristic curve. Finally, to measure image degradation, we use the peak signal-to-noise ratio and the structural similarity index measure. Large values of these metrics indicate high quality. Here we report the COCO key points evaluation results and the average of the image quality metrics among all images from the COCO validation set. In the first row, we show the results for the traditional non-privacy preserving OpenPose network without considering the face key points as our upper bound. Now, we show the results when using a defocusing lens and low-resolution cameras. As observed, in both approaches, the image quality decreases and the human pose estimation has a poor performance. Finally, our proposed optimizer lens achieved the best results since we obtained a lower image quality and a better human pose estimation performance. Now, we test the robustness of our acquired images to non-blind deconvolution attacks. This is the worst scenario assuming that an attacker has access to the camera. First, let's consider a defocusing camera. If the attacker knows the PSF, then he can train a state-of-the-art non-blind deconvolution to reveal the identity of the boy. Now, let us try with our camera. From the PSF, it is observed that our lens has more aberration than the focusing lens. If we try to perform the convolution, then our prepaid images prove to be more robust. Here we show some qualitative results of our method. The first and the second row corresponds to an RGB image from COCO validation set and the human pose estimation respectively. Now, these are the acquired images using our designer lens and the corresponding pose estimation results on the same images. Here we perform frame-by-frame detection and compare our designer lens with the focus and low-resolution cameras. Finally, to experimentally evaluate the effectiveness of our proposed privacy-preserving approach, we built a proof-of-concept optical system shown in the figure. The prototype comprises a main objective lens coupled with a 4F system, a Canon camera placed at the optical setup image plane, and a deformable mirror to generate distortion. This optical device can be parameterized with up to 15 Cernic polynomials, which limits the level of distortion of the scene. We first simulate the system and then load the Cernic coefficient to the deformable mirror. After calibration, our prototype with the deformable mirror creates an optimized PSF that closely resembles the simulated PSF. Then we acquire the degraded image with our prototype in the lab and perform human pose estimation. In this work, we introduce a privacy-preserving end-to-end optimization framework to design the camera lens and perform human pose estimation on degraded images. We design our privacy-preserving lens by adding aberration using Cernic polynomials. Furthermore, we build a proof-of-concept optical system and our experimental results in hardware match the simulations. During inference, we can deploy our system in hardware by constructing a camera lens using the Cernic polynomials we learn and running our privacy-preserving human pose estimation network. Also, we can deploy a less secure system as a software-only solution by implementing the image degradation post-acquisition.